on? I'm on? Yep. Hi, good afternoon, everyone. Firstly, big thank you for you all coming along this afternoon. My name's Steve. I'm a Microsoft MVP, Pluralsight author and engineer at Elastic. Today we're going to be talking about writing code with code. Specifically, we're going to look at something called Roslyn. Before I move off this slide, I do want to highlight there's a bit.ly link there. So if you want to access the slides after the session to recap anything, if you've got that bit.ly link written down, you'll be able to do that. I'll show it again at the end as well. If you have any questions that we don't get to today or during the rest of the conference, then you can find me online. I'm at Steve J. Gordon on most social media. Possibly wanted by the police. And I blog at stevejgordon.co.uk as well. So some of the stuff that I'm going to cover today is also covered there on my blog. So just to go through what we're going to talk about, just so that everyone's expectations are set, the first thing we're going to do is introduce Roslyn. So there's no need to know what Roslyn is before this session. We'll go through some of the basics, and then we'll start to explore some of its APIs that we're going to use to ultimately build something called a syntax tree to generate some C# code. All of these sort of bits that I'm going to be talking about are grounded in a practical application that I had to co-generate a new version of the client for Elasticsearch. And so I'm going to talk a little bit towards the end about the specifics of that around how we came up with a schema to define what that API needs to do, how we transform that spec into something that we can sort of define in a strongly typed language like C#, how we build up the syntax trees, emit the C# source files, and ultimately what I've learned along the way. So let's begin with Roslyn itself. So Roslyn is actually a code name. It's a code name for a project that Microsoft kicked off in around 2010. And normally Microsoft are pretty good at coming up with good code names for their products and projects that they're working on, and then giving them a really sort of bland, boring Microsofty name when they release them. Roslyn's actually stuck. So if you search for Roslyn and .NET, you will find the documentation, you'll find the GitHub repository, you'll find sort of examples and blog posts online. So that's great. Microsoft couldn't resist, though, giving it a Microsofty name as well. So you may occasionally see it referred to as the .NET Compiler Platform SDK, which just runs off the tongue. But it's worth knowing that because it does appear that way in a few places in the tooling. So this, as I say, kicked off in 2010, was finally released in 2015. So what is it? So ultimately what Roslyn is a set of open source, open box compilers, specifically for C# and VB.NET. Open source is pretty self-evident, so this code is up on GitHub. You can view it, fork it, modify it, and contribute back to it as well. That's actually quite easy because one of the things that this project did is rewrite the C# compiler in C#, which sounds a bit like Inception. To compile the compiler, you use the compiler that you've just created. But this is useful. This is a way of testing languages and their maturity, because if you can write something that's a relatively complex system like a compiler using the language, then you know your language is pretty capable. It's also a great way for the team to dog food their language. They can test what it's like to write the C# code, and they can look at possible enhancements that they might want to make that makes writing that compiler code more terse or more sort of readable. The open box part is also pretty useful. So traditionally, compilers have been quite closed box systems. You put a bunch of source files in at one end, you get back some kind of executable or binary, DLL, some kind of output. But what happens in that middle phase is pretty opaque to the user. What the Roslyn compiler system does is open that box, and it gives you access to the various phases that the compiler goes through in the form of APIs that we can use to access the metadata and the information that the compiler has, because the compiler knows a lot about our code. It has to in order to compile it. So it knows about the syntax, it knows about possible errors, it knows about the semantic meaning of the code and how all of the symbols are defined and relate. And so that's why this is referred to as a compiler platform, because we're given now access to all of those APIs to work with different phases of the compiler if we need to. And this is something that's used heavily in tooling like Visual Studio to drive some of the features that we use daily. I summarize it as kind of like the maker of the squiggles and the finder of the things. It does a lot more, obviously, but the squiggles are a kind of thing that we've probably all seen in our code. I mean, I'm sure you get less red squiggles than I do, but you see a squiggle, it usually means that either there's an error, so maybe you've made a syntax error, you've missed a semicolon, or you've got too many braces, whatever. That's something that the compiler can detect because it parses the code and it understands the syntax that you've provided it. But we get squiggles for other things. We get squiggles that give us suggestions for how we can improve our code by maybe refactoring it or moving to newer C# language features, or maybe applying rules that we've defined in things like an editor config. Finder of things is things like going to definition or find all references, the ability to kind of navigate through our source code and the symbols that we've defined within it and find how things interrelate with one another. There's another feature of Roslyn that we probably also use daily in our code bases. It's analyzers. So these are built into the .NET runtime, but you can also bring in analyzers from NuGet packages or build them yourself and within your organizations. So an analyzer is ultimately something that basically contains some code that recognizes a violation of some rule within our code. So what that rule can be is pretty much anything that you could infer after parsing the code and understanding the syntax and some of the semantic meaning. So it can be things around the coding structure that you want to enforce, maybe a coding style, maybe even things like how you want things to be named. A lot of this can be controlled through simpler methods like editor config, but for certain scenarios, analyzers are a great way to go. The other side of this is the code fix. So if we can detect that there's an error in the code or something isn't being done right, that's one nice feature. But what's really useful is that if we've got a fixer for that, we can automatically update the code behind the scenes to apply that change. So as developers, we can be less concerned with all of those minor improvements that we need to make. We can just have the tooling make changes for us. So as I say, you can ship or build these yourself and ship them within your organization. So if you really wanted to mess with colleagues, for example, you could have an analyzer that checks all class declarations in your code base and make sure that they don't have the word builder in them, for example. Anything you could possibly think about around what the code looks like, you can potentially flag up. So just to see what analyzers look like in action, I'm going to jump over to an example in this repository. Good, that's up on screen. Hopefully that text is clear enough for everyone at the back. Cool. So the code here is completely unimportant for the demo. This is part of our Elastic Transport library. There's a method here that's doing some stuff. But the bit I'm interested in is this write async call here. So on here at the moment I've got an await keyword, which makes sense. If I remove that, I immediately get a red squiggle underneath my code. And if I hover on that, I get told that this is being highlighted because the call is not awaited. Execution of the current method continues before the call is completed. Consider applying the await operator. So this identifies a potential common mistake that you could have if you forget to put the await operator on here. For most scenarios, that's what you want to do because you want this thing to complete successfully first. In some scenarios, you might have fire and forget, and you would want to ignore this. But for most scenarios, this makes sense. And you see we get this little tooltip here, this kind of screwdriver. So if I can click on there, I can apply the fix for that, which then puts that keyword back in. Another example is down here. So if I remove the configure await false here, which we don't have time to go into why that's useful in libraries, but we're doing it here, and you can see I get another squiggle. And this time, I'm getting this possibly missing configure await false. This has got a code here, CAC001. So this one isn't coming from the .NET framework itself. This is coming because I've got an external NuGet package pulled in that's adding this feature. So again, I'll just let it apply the fix quickly, and I'll show you where we reference that package. It's just a regular NuGet package here, this configure await checker analyzer that we're referencing in all of our projects. So that just enforces a rule that we want to have within our specific code base here. Close that down, save some memory. Right. So that's kind of analyzers and fixes in action. Another cool feature that's a more recent feature of C# and Roslyn is source generators. Now, I'm not going to go into depth in source generators. They can and are a whole conference session of their own. But I will sort of highlight what these are. So these were introduced in C# 9, so around .NET 5 timeframe. And what they ultimately do is provide us a compiler feature that lets developers inspect the user code while it's being compiled. Now, that statement alone is probably not enough to really explain their benefits, so I'll go on. So what we can do once we have source generators is we can develop these components that run during compilation, and they have access to all of the metadata about the user's code, the application code. So this is the syntax and the meaning of that code. Now again, you might be wondering, is that useful to me? What it lets us do is inject C# source files directly into that compilation that's happening. So we can build up new C# source files that become part of the compilation. So logically, when the compiler starts, it parses the code, understands what's there, and detects if any source generators need to be run. It runs them. That might produce some additional sort of virtual C# files that are now going to be part of that compilation. And then it finishes doing the whole compilation with those new files included. And where this can be really useful is doing things that either reduce sort of manual repetitive code like following patterns, or maybe optimizing code for scenarios that sometimes have an impact at runtime. So for reducing boilerplate, one example would be if you're doing sort of the MVVM pattern and you're using iNotify property changed, you know that that interface is relatively straightforward to implement, and it's just boilerplate that you kind of have to follow a pattern anywhere that you need to use it. There's actually a source generator provided now in the MVVM toolkit that just allows you to put an attribute on your code, and it does most of that heavy lifting for you. So it's a bit of a time-saving effort. Another example is doing high-performance logging in ASP.NET Core. So the logging features in iLogger have an optimized mechanism for how you write those if you want to have a low allocation code pass for your logging. Doing that manually takes a little bit of effort. Most people wouldn't bother doing it. But with the source generator, you can actually get that same effect with just a new attribute on your code, which makes things a lot easier. The other scenario is that optimization of code at runtime. So there's certain scenarios where there are slower paths in our code at runtime because we need to know things about the code. And a typical example of that is serializers. So something like system text JSON is a library that Microsoft write, and it needs to be able to serialize code to and from JSON to types that the application is going to define. So it doesn't know what those types look like. So the only way it can access that information is to use reflection. And it uses reflection the first time a new type's being serialized to find all of the properties on there, to find all of the JSON attributes, and figure out how it's going to serialize and deserialize that thing. Now that work happens, historically at least, happens at runtime, and it's a small performance penalty that first time that type is serialized. With source generators, because they have the same information at compile time, that can run now ahead of time during compilation. So the source generator can inspect the code, inspect all of the types that have JSON attributes, and figure out how it would serialize those to and from JSON, and spit out the code needed to do that ahead of time at compilation. So there's no longer a runtime cost if you use the source generator for JSON serialization. Now this isn't a full session on like compiler theory, but I do want to highlight the compiler pipeline that Roslyn has. It's a pretty familiar pipeline to most compilers. The first phase is parsing. So ultimately, source files are just text. The compiler needs to interpret that and work out, well, what are the language keywords that are in here? What are the structures and the declarations that are occurring within that code? What's the syntactic and the semantic meaning that's being defined in there? So parsing is that process, and ultimately it's going to build up something that we'll look at in a moment called a syntax tree. The other part is identifying all of the symbols that we define in our code, all of the types and the properties and the methods and things, including those that we import from NuGet packages, and also binding those to all of the other components in our code. So what is the type of a resulting expression in our code? What is the type of a variable? Binding that information back to the symbols. And the final phase is emitting the IL code. So most C# and .NET applications, VB.NET, F# by default will compile to IL code, intermediate language. IL is this middle ground between the high-level C# code that we write day to day and the low-level machine code. And what's nice about it is it's entirely cross-platform. So if we compile a DLL on a Windows machine, we can still execute that on a Linux machine, because the IL code is only actually interpreted to the architecture and the platform by the runtime when it's first needed. So this is called the just-in-time compilation process. Just-in-time because methods only get compiled as they're needed and accessed. Now, of course, more recently, it's becoming quite popular to consider doing ahead-of-time compilation. And in that scenario, the JIT is not involved. We don't just-in-time compile. We compile our code directly into machine code for a particular target architecture. So in that scenario, the IL phase would be not required because we'd be going straight through to the actual runtime code. So the Roslyn API includes various different sort of API levels that kind of roughly align with those compiler pipeline phases. And this is what gives us access to those different capabilities and those different types of information that the compiler builds up about code over time. We're specifically going to be focusing on syntax tree API for the rest of the session. So what are syntax trees? Syntax trees are basically the result of that parsing and analysis phase that the compiler is going through when it first reads our code. So as I say, C# files are nothing more than just a text document. They contain text. It just so happens that it conforms to particular specifications that make it valid C#. So the compiler's first job is to parse all of the individual elements in there into the tokens that make up that file. So it's things like identifying all of the keywords, the language keywords that have been defined and used, all of the identifiers and things that people have used, so all of the declarations of things that occur within that code base. Ultimately, then, it builds up this tree representation, which is the syntactic structure of the code. So it's represented by three main elements. There are nodes, which basically are the language constructs, if you will. So there's a construct, a declaration for what a class looks like, what a property looks like, what a method looks like. Those are the higher level concepts, and they're defined as syntax nodes. Syntax nodes can have child nodes below them that belong logically within them, and they can also have tokens attached to them that provide additional information. So by default, a class declaration syntax node doesn't have an accessibility modifier applied to it, but you can add one by adding a token. And in this case, that's just adding the public keyword or the internal keyword at the start of that declaration. And so those pieces of information get picked up by the compiler and attached as tokens within the tree. Tokens are essentially the terminator in the tree. They don't have children directly, but they do have something called trivia below them. And this is optional additional information that isn't relevant for compiling the code, but it's information that is contained within the file. So it's things like, where is the white space in the file? What are the new lines within the files for how it's formatted? And it's also things like code comments or XML documentation comments. Those aren't needed to compile the code, but they are useful pieces of information contained within the C# file, and therefore they get represented in the syntax tree. So once we have a syntax tree, it gives us this capability to interact with our code on a more deeper, meaningful level, because it's no longer just a text file. We now have this data structure that represents all of the elements that we've defined within our program. And so if we want to start using those APIs, we can do some slightly advanced things with them. Now, there's two important points to highlight about syntax trees before I go on. So the first is that all of the nodes, the tokens, the tree itself are immutable structures. It's done in as an optimized way as possible, but the main reason it's done this way is to ensure thread safety. Because the compiler and all of its APIs and all of the state about the syntax tree may be accessed by multiple threads. If you imagine an IDE, it's checking lots and lots of things about our code at the same time. We don't want any changes to that state to cause sort of threading issues. So anytime you work with its elements, if you make changes to them, you create a copy with the changes applied. The other important fact is that it's round trippable. So we can parse a C# source file, and as a result, we get the syntax tree that represents it. And because we've got that syntax tree, including things like the trivia about the white space and the new lines and the comments, etc., we can entirely reconstruct a C# source file directly from that syntax tree. So that's kind of nice. We can take a C# file, parse it, and then return it to a C# file. But what we can also do is use the API directly to, in memory, define a syntax tree and then have that emit a C# file that represents what that describes. And so that's what we're going to basically see as we move through the rest of this session. So to work with this in Visual Studio, I want to show you a couple of things just to help visualize this concept. So there is some tooling in Visual Studio to help us with that. So this slide is probably a little small, but hopefully you can kind of see it. I'll describe what it's showing. What we're doing here is adding in a workload for the Visual Studio extensions development. And the reason I'm adding that is because on the right-hand side here, you can see it includes the .NET Compiler Platform SDK. So that's the Microsofty name for Roslyn. So we're adding in the components there needed to work with Roslyn and view some of its features directly in the IDE. The other thing that I've added for the purpose of the next demo is a thing called the DGML editor. This is just an individual component you can add in, and you'll see what it does in a moment. So let's take a quick look at a demo of what it looks like to visualize syntax trees. So I've got a very boring, unexciting program file here. So this is an entire program. It's in a namespace called examples. We have a program class, main method, creates an instance of a data type, writes some data out. The code itself is unexciting and uninteresting, but it hopefully is basic enough to demonstrate the concepts that I want to show. So the first thing I want to do is visualize what the syntax tree for this code looks like. And I can do that because I've added in that .NET Compiler Platform SDK feature. I can open up this other window here called Syntax Visualizer. And I'm hoping this is going to be big enough, if I pin it, big enough on the screen. We'll see. So if I now open this and click anywhere within the code, you'll see that this side refreshes here. And I'm just going to collapse this down so we can see what it's showing. So at the top here, we've got this logical thing called a compilation unit. That just logically represents a C# file. It's an input to the compiler. And you can see indented under that, because it's part logically of that as a child, we have this file scope namespace declaration. And we can see that we've got a file scope namespace declaration at the top of this file, and that's represented here. So this blue represents a node. So this is a sort of language construct in the syntax tree. Indented below that, we have more elements, and that's indented because logically a file scope namespace declaration encompasses everything within it in the file below it. So everything belongs to this namespace and therefore is a child of it in the syntax tree. And so we can see that this file scope namespace declaration here is made up of this namespace keyword, which if I click on this here, highlights over here, tells us, you know, the character's position in the file as well. And you can see that this namespace keyword, which is a language keyword, therefore it's a token in the tree, which is green, also includes trailing whitespace, which is the space character that follows it. So you can see the tree is very, you know, verbosely describing our code here. We then have this identifier name syntax node, and in that we have a token, which is the logical token that represents the identifier for the name of this. So this isn't a keyword, this isn't something C# specifically knows about, it's something we've defined as part of our declaration. It's followed by a semicolon token that has here end of line trivia that is a traditional sort of pattern that we would have a new line after a semicolon, and then it goes into the class declaration. If I just expand the internal keyword of that class declaration, you can see this one has leading trivia, which is this new line here, and then trailing trivia, which is the space after it. So that's a way that you can kind of start to understand syntax trees and what they look like in representing your code. Because I installed that DGML editor, the other thing I can do here is right-click on this, this particular node and say View Directed Syntax Graph. And if I do that, I'm going to get a new window, which I'll zoom into. And this really is just a graph-based representation of that same tree. It's just a little bit easier to sort of see in a visual nature the entire tree. And you see that's a relatively simple C# file. There's only a few lines of code in there. But already we've got a very complex and rich syntax tree that knows everything about what's in that file. So again, you can see, you know, at the top of this we have this file scope namespace declaration. It's got some children. One of those is the namespace token, one of them is the identifier, and we can see the trailing whitespace in grey and leading whitespace in white here in these boxes. So if you want to start learning what the syntax tree and what the different nodes are, this is one way you can go about that. So I'm going to talk a little bit more now about the practical use case of some of this information. So the reason I started looking at this API and started learning about things like syntax trees was that through my work on the Elasticsearch language client for .NET. So this is something I sort of joined the team about 4 years ago and took over the language client. I've moved on from there, but one of the jobs I had during those kind of 2 years that I was on the team was thinking about how we would move to the next generation of client. So Elasticsearch itself is a very rich service, and it's entirely managed through REST-based APIs. So everything that you can do with Elasticsearch, you do through that REST API. That's include, you know, things like indexing documents and searching them back, but it's also managing the server, checking its health, setting up how you want to map data, etc. And over time, that's grown from a small number of tens of endpoints to well over 420 endpoints now. And to represent all of the data in and out of the endpoints, there's over 4,000 data structures involved, all of the different requests and responses, all of the sub-objects that they may need to contain. There's some fairly rich JSON structures that you might need to send in and out of Elasticsearch, including things like all the specific queries and aggregations you can perform. And so one of the problems for the V7 client, which is the previous version of the client and Elasticsearch, was that it was almost entirely handwritten. Small bit of code gen, but mostly handwritten. Now, in the early days of Elasticsearch, sort of when the client was first created 10, even 11 years ago, that wasn't too much of a headache because there were only tens of endpoints and it wasn't evolving that quickly because it was a small team. But now Elasticsearch is a much larger company. We've got a huge number of people working on the product, adding new features, and the API evolves very rapidly in each minor release. And that means that for a single language client developer, it was very hard to keep pace just with those API changes, just checking what's gone into the server and remodeling that on the client so that you can interact with the API and all the new endpoints or changes to endpoints. It also meant there was a lot of just maintenance work, just keeping track of those things. And it meant that a lot of my time wasn't spent doing what I wanted to do, which was value-add features to make it easier to work with the client, to document things better. It wasn't really happening because I was spending all my time just kind of keeping pace with Elasticsearch itself. So for V8, we needed to address this. And one of the things we wanted to do is think about what the new generation of a language client for Elastic would look like. And the main thing is that we decided that they needed to be code-generated. We needed to automate a lot of the code writing part and allow us to focus more on the higher level concepts, the usability of the API, the documentation, thinking about features like helpers that can make it easier to do certain things within Elastic. And so we decided we'd do this based on a formal spec, and we'll get more into that spec later. But for now, imagine that you're given this sort of when you go back to work next week, your manager comes to you, they say, we're going to give you this JSON spec, don't worry too much about the structure of it, but it's going to define some types that you'll need to define in C# and the properties that they have and various information that we want you to generate. What are your options for code generation? The most simple that comes to most people, and it's a valid approach, is just using strings. Like you could just logically build up a string that represents the entire contents of the C# file. You could do this with String Builder to be slightly more efficient, and you can have placeholders for anything that's kind of varies. So you would logically define, what it looks like to define a class, and maybe have a placeholder for the name. And that would just be a string that you concatenate with the next part of the class definition. That's fine, it works. It's not particularly efficient, but code generation doesn't necessarily need to be. But it is open to sort of error. If you make a typo in the string, you're not going to get any sort of identification that you've made a mistake until you generate the code and then try and compile the generated code. So it doesn't give you a great feedback. Templates is kind of the next step. It's a slightly better scenario because now, once you get your template that represents what your C# file and a class needs to look like logically, you can just fill in the blanks by passing in some kind of model. So that could be something like T4 or even something like Razor. In the V7 client, the low-level components that we did code generate used Razor, which is an unusual use case for it. So instead of like Razor, where it's traditionally used in MVC for views and models that you're rendering to a web page, for us, the view was the representation of the structure of a C# file. So we'd have, public class and then a placeholder that would get filled in from the model. The model we built up from the information that's contained within the spec, and then we just let the model binding of Razor kick in and produce the resulting file that we needed. That's kind of nice. It does avoid some of the risk of repetition. It's a little bit easier to code against because you can see the structure of the thing that you're about to generate rather than just having lots of strings that you have to try and piece together in your mind. The third option, and it's not necessarily the definitive list here, but the third option that I thought about was Roslyn. So I knew Roslyn existed, I knew it had APIs. Could these be a solution? And so just as we can parse that C# source file to the syntax tree, as I said, we can create a syntax tree in memory. So why not do that? Why not use its APIs to build up a valid syntax tree and then have it produce the C# file? And so I'm going to give you a quick demo of what that looks like in code. So if I come over to save this. If I come over to this file, so this file normally, this is a horrendous font size, but on a normal screen this pretty much fits on one screen, and it's the entire code needed to code generate something from a basic spec. So I'll go through what most of this is. This first portion actually here, all these first lines are all just about reading the spec itself. The actual code gen is only a few lines here. So the spec that I'm using is a very cut down version of our Elasticsearch specification that we'll go into more detail of later. But all this spec does is just define some types that we want to code generate and the properties that they have. So the only information we know about the types is what the type name should be and what its properties are. And for a property, we obviously need to know what is the type of the property and what's the name. So that's like the bare bones, smallest spec that we can sort of come up with. The project itself has a package reference here to this. This is yet another name that you need to know about. So this brings in the Roslyn APIs for the compiler platform, but it's under this Microsoft Code Analysis C# NuGet package. So this lets us work with C# files and the syntax trees in code. So the first piece of code here really, as I say, is just reading the JSON file, deserializing it into this strongly typed representation of what the spec file defines, which is just a collection of types. Each type has a name and a collection of properties. The property have a type and a name. So that bit's pretty basic. But the actual generation code starts here. So this is where we start to create the syntax tree pieces. So in this case, what we do is, for all of the types, we do a select here, and for each type, we're going to generate a class, or class declaration. So this result here is a class declaration syntax array. So it's a set of declarations about all of the classes we want to produce. Create class down here. It's pretty straightforward. It takes the name of the class and its properties, and then we call this factory method here to start defining that. So this is available, as you can see, it's part of the SyntaxFactory, which is the preferred way of building up a syntax tree and its nodes and its tokens, because it enforces constraints around how you model those things. You can actually new up a class declaration syntax object yourself if you want to, but it's recommended that you use the factory. This is available to me because I've got the static using up here for the SyntaxFactory, so I can just call this method here. So what this does is say, okay, I want to define a class declaration. For a class declaration, the minimum thing we need to provide is the identifier for the class. And so in this case, that identifier is coming in as the string here that we added to this syntax token, this identifier. This gives me back a class declaration syntax. As I said, we need to then provide any additional tokens that modify the declaration. So in this case, I'm adding a modifier, which is the public keyword token. So this says, okay, I want this to be a public class declaration. Next, I iterate through all the properties. For each property, I call add members to add members to that class declaration. In this case, our member is a property declaration. Again, this is coming from the SyntaxFactory. This needs an identifier name for the type and an identifier token for the name of the property. Again, I'm going to make it public here, and I need to define the accessors that we want on this property as well. In this case, the get accessor with a semicolon token after it, and then the set accessor. So it's quite a verbose way of defining what the code needs to be in the syntax tree. I will point out I'm using these add methods here. There is an alternative which you can use, which is something like with modifiers or with members. If I do with members, or is that not one? With accessor list, for example. And you can see what this takes is this accessor list syntax. This approach just results in more verbose code. So I tend to avoid the with methods and prefer the add methods because they're just terser for defining code. The other important point here is this reassignment. So this code would be valid, or looks valid, if I do that. I'm adding members to this class declaration, I'm returning it. The problem here is the immutability. So because everything like a syntax node, a class declaration syntax is immutable, when we call add members, we don't modify that instance referenced by this variable. We get a new one. This class declaration syntax we get back is a new copy with the change applied, with the new member added to it. And so if I want to be able to return that later on, I need to reassign my local variable each time, remembering that we're working with immutable types here. After defining the class declaration up here, we get an array of those. We then create the file scope namespace declaration, and to that we add as members all of those class declarations, and that's all we need for a minimum scenario here. Next thing I do is open a stream to where I want to generate my file. And then you can generate to a file from any node in the tree. So here I'm just using that namespace declaration, and I'm calling write to the stream. So if I run this code, hopefully it will run. It should be pretty quick. I'm going to open up Visual Studio Code here. This is the code window in the location where I'm generating to. Minimize that. But after that runs, we get our generated file. And if I jump into that file, you can see it's not exactly what we were hoping for, but it's close. So we do have a namespace code gen, we have the public class defined, we have the pieces that we'd expect to see, but this is not valid C#. A parser can't parse this because there's no spaces. It doesn't know what's a keyword and what's an identifier and what's in there. The problem here is that we haven't defined any trivia on our tree. So when I go back here, there's a couple of options to this. Well, there's three main options. One is that we can add trivia to any token that we want. So we can do with leading trivia here on our public token, and we can add a new line before it or a space after it with a trailing trivia. That would obviously get very verbose, because every space, every new line then would need to be defined. Another option that's really simple and just gets us going for demo purposes is we can call normalize whitespace before we write this out. And this will add basic whitespace rules that C# has around spaces after tokens, new lines after semicolons, etc. It's not very rich. It's good for sort of demo. You tend to evolve from this to using a formatter where you can provide specific rules for how you format your code. And that can even be driven by passing in an config file that contains the formatting rules that you want to apply to your code base as well. But I'm just going to stick with this one for now. And I will rerun. Did I close the program? I bet I didn't. No, I did. And I'll run this again. And this time if I go to the output directory, it's a bit too huge. If you can see there, we have a valid C# file now. We have a class, we have a property on there, we have an empty second class here, and it's good enough. This would parse and be valid C# that the compiler can run. So that's the very basics of things. I'm going to copy this code and just show you a big cheat that's really useful. Trying to understand how you build up this work with this Roslyn API to write the code is quite painful if you first start doing this. This site is where I spent a lot of my time in the early days. Roslyn quota azurewebsites.net. So what this lets us do is paste in some valid C# code, and then just go down and click a button. And once it runs, it will give us the Roslyn code using the Roslyn APIs that's needed to generate that, which is a big time saver. The main difference here, it's longer than what I wrote myself, and you can see that's because it prefers the with methods. And so you end up with this create with members, which needs a list of members, which is created from a new array. So it's not particularly efficient code. It's not terse enough for what I like, but it does functionally work. And so that's one way that you can kind of say, well, here's a snippet of something that I want to be able to code generate in its sort of templated form. Let me see what APIs I need to call, what declarations I need to create to do that. We could even, if we want to, ask it to preserve original whitespace here, and now you can see it's going to be way longer, and that's because it now manually puts all that trivia in. And this just is an example of why you wouldn't really want to be defining trivia manually in your code yourself, unless you're sort of a glutton for punishment. So that's generating some code and basic examples. So the next thing I want to do is then talk about the practicalities of what it looked like to start working on generating the .NET client, because it's obviously a bit more complex than that little example I showed you. So the first thing that we need to think about as a team was, well, what spec have we got that defines Elasticsearch? We need to know about all of its endpoints and all of its types that are sent in and out to those endpoints in order to be able to define, a language client that lets you interact with those. So the first thought, because this is a REST-based API, the first thing that might start coming to people's minds is OpenAPI, right? This is a spec that's already sort of a way of specifying RESTful endpoints already, and it's probably a good choice for simple scenarios. At the time this project kicked off, which was over 4 years ago, OpenAPI was just too limited to express everything we needed to about Elasticsearch's API. Our main problem was not really defining endpoints themselves, it was defining those types that go in and out as the search requests and search response, the requests and the response bodies. Because those are complex data structures, some of them involve like polymorphic types. There's some sort of real quirks of Elasticsearch where it can take and receive a union of things. Some of those are really hard to define. And if you can imagine the idea of maintaining in YAML or JSON manually 420 endpoints and 4,000 data structures, it wouldn't be particularly fun. So we as a team wanted something that was kind of a bit of a middle ground for us to work against, and we landed on TypeScript. So TypeScript already has a TypeScript system that allows us to do things like static type checking, and it's designed and built to represent JSON and JavaScript quite nicely. There's a lot of tooling around it. It includes features like inheritance and generics, so we can define these more complex concepts more easily in a sort of intermediate form that we can all work with. It also has its own compiler platform APIs as well, so that you can hook into its syntax tree or through its compiler pipeline as well. And there's a library called TSMorph that we relied upon to do some of the compilation at the end that we'll talk about. So what does our actual spec kind of look like? It's a little outdated now, but it's still kind of pretty relevant to how I was generating things about a year or so ago. So this, in TypeScript, represents a search request. It's a search request because it's logically going to be below a search namespace that we don't see here. And it also has this meta information that we attach in the code comment here through these @ tags. And these are things that our compiler for this spec will know about and be able to use. So in this case, it's defining the search request. It's been Elasticsearch since day one, so hence 0 onwards. It's a stable API. That defines the meta information about the endpoint. And then we also have the request type itself. So there's various parts of a request that I want to talk about. On a request, you can have path parts, which are in the URL. You can have query string data, and you can have, obviously, a body. And Elasticsearch uses all three elements in various ways to give you different options for how you perform a search or how you perform a particular operation. So in the case of search, we have path parts, and in this case, we have a single path part named index. It's optional because of the question mark, and this is logically where we can, where Elasticsearch lets you limit your search to a particular index or set of indices. And so this is optional because you can perform a search against everything and you don't need to provide it. But if you want to limit to an index or a data stream set, then you can do so. And so the way we've modeled this in the TypeScript is we said, well, okay, it's optional, it's of type indices, which itself is a union of either an index name or a set of index names, an array. We define it explicitly there with a union. In C# you'd probably say, well, you just have an array or a list, and it can contain one or many things, and that's kind of fine. But here we're being very explicit. This API accepts one thing or many things as an option. And then the index name itself is this kind of alias over the string. So it just represents a string logically, but it allows the code generators to attach additional logic to that if they need to. I'm going to skip over query parameters. The body here defines all of the possible properties on the search request body. These are all optional. You can see question marks, so you don't have to provide a body when you do a search. But normally you attach certain things that you want to control that search request. So here, for example, aggregations is defined as one of the possible things you can do on a search request. Aggregations, through a quirk of the design of Elasticsearch, can either be passed in the JSON either through a property named aggregations or just ags. And so we need to be able to model that. So we do that again through these kind of alias tags in the model. And then an aggregation in Elasticsearch is logically just a dictionary, and you provide a string which names the aggregation that you're performing, and then you provide one of many possible data structures that's a valid aggregation for Elasticsearch. So this is where the polymorphic nature of Elasticsearch kind of comes in, and we'll see what a container does in a minute. But we also have here like regular code comments, and these can be used by the code generators to add in sort of like XML documentation comments in the case of the C# generator. Search response is pretty much the same idea. Here we've got a response, and we have a response body on that response. And you can see here we've got generics, so that's useful because a search response is going to include data in the JSON that is stuff we don't know about in our model here, because it's going to return to you the results, the actual user documents that you've searched. And so we can use generics in TypeScript to represent that potential nature. And so the response body adds a bunch of stuff on it, but one of those is the hits. Hits is of types hit metadata. That includes things like the total, which again is another union scenario where it might return you just a long, or it might return an object that represents the hits information. That's controlled by your search request itself, so how that comes back is controlled by the request. So we need to model the scenario that this response could include either of those. And then in the actual hit itself, which is hit of tDocument, you can see we've got the source, which is the actual result, the actual data that you've searched coming back. The rest of that's the kind of metadata about how it's scored in the search and its ID and things like that. But that's how we model the requests and responses. For those polymorphic scenarios, we use this concept of a container, which isn't a real object on the end of the server, but it's a logical construct that we have in the TypeScript here that's going to represent that this thing could be one of many things. And so for a query, when you do a query against the search endpoint, you could provide a bool query, or you might provide an exists query. And so we just model all of the possible query options that we know are valid here. And we use this variance tag here to identify that this is a container which contains all of the possible variants we know about. It's non-exhaustive because custom plugins and things can add custom query types that we might not know about, so we allow for the fact that the generated code has to be flexible enough that you could provide a custom version of one of these as well. Now, once you've got a spec, how do you test it? How do you make sure it's aligned to the server? We could have written a bunch of tests ourselves, but that would have been really painful. So we just cheated a bit, and we piggybacked onto Elasticsearch's own integration test. We wrote a thing called the flight recorder that runs and collects all the requests and responses during the integration tests that occur as part of the Elasticsearch build, which is some like 5,000 plus tests. And so this means we're hitting all of the possible endpoints with various different search bodies and getting back various different search responses. And all we do is record the JSON parts of that and then just check it can be serialized to and from the spec that we've defined in the TypeScript. So if something comes back that we haven't got as a property on our TypeScript, that's going to be an error because we don't have a property for it, so we need to add that. Or if we've got something that's marked as required, but it doesn't occur in all the responses, that's obviously wrong in the spec. It should be marked optional, those kind of things. And so these run as part of our PR process. So if someone submits a PR to the spec, it works out all of the endpoints that type's used in or against, runs or gathers the JSON that's recorded from the integration test and then validates it against that new change that's being made. Once we've got a valid spec, we need to generate something from it. So at the moment, everything's defined in this TypeScript. And so the first possibility, because we're now getting all excited about sort of compiler APIs, is that we could actually hook into TypeScript's own compiler and access its syntax tree and start piecing together enough information that we then take to generate the C# syntax tree. The reason we don't do that is it's quite low level. Each language client generator would need to know how to parse, TypeScript's syntax tree and work with its API. And it's also not constrained enough. There's things that could be inferred from the TypeScript code which aren't sort of fully modeled yet. And we wanted to be able to sort of tighten that down with a simple metadata model. So what we do is, as part of the compilation phase of TypeScript, is generate a simpler schema, which is a JSON file. Say simpler, it's some 200,000 lines of JSON, but it's a model that's tailor-fit to the needs that we have of all the things we need to know about endpoints and the types, and it's unambiguous. It has a set of rules that as long as you follow them in a certain pattern when you're generating the code, the Java code and the C# code will be roughly aligned in terms of how they've modeled things. And so what we do as part of our code generation pipeline is we have the TypeScript files that we're creating that represent all of our types, that represent what the Elasticsearch endpoints accept. The TypeScript compiler runs, and then we hook in using that TS-morph library a phase where, rather than generating a typical output of TypeScript compilation, we want to generate our schema file. And so we take all of the information that we can then read from the syntax tree during that compilation phase and spit out this JSON file. And that includes all of the endpoints, all of the request response bodies, all of the types in the JSON. And so that's then the input to the C# language generator that's going to spit out the .NET client. And of course, we'll have other generators, and we have ones for Java and Go and Node that generate those clients as well. Now, obviously, dynamic and static languages will have different challenges in how they model some of these things, but each of them have a strict meta model in the form of that schema to use as their starting point. We also plan to take that further as well. So one of the things our docs team needed was an open API spec for Elasticsearch that we didn't have. Well, actually, our schema JSON is kind of a superset of that information, so we could actually code generate the open API spec from it. And in the future, we could even get spec driven. So right now, the Elasticsearch team make a code change in the Java code base for Elasticsearch, and then they update the schema or the TypeScript model that represents what they've just done, the new endpoint or the changes to a particular type. Now, obviously, that has a risk of getting out of sync if they forget that phase. And so what we could do is have them actually just update the schema in TypeScript that they want to define, and then have that even generate the Java code base for Elasticsearch as well for the request response side of things. So I'm going to have just a quick look at the schema JSON that actually gets generated, the real schema JSON. I've got some cheat line numbers here because it's a huge file. So this is the file, as I say, it's like 212,000 lines of JavaScript or JSON. I'm going to go to this line number here. So this is where the definition for a search endpoint appears in this file. So we can see that this is available in our serverless product as well as our main stack. We have a description for it. We have the doc URL for it. We know its name, what privileges are needed to run it. And then we know what its request type is. So the request here is this request type defined in the _global.search namespace. It's not required. It's application JSON. And then we have the URLs for this. So there's two possible URLs. This path, which searches against everything, or this path where we use that index path part that's defined in the model to have a placeholder for one or many indices that we want to search against. Both of these accept get and post. I'll just get my other line number here. Lost my place. So this is where the search request body JSON starts to appear. So there's a lot of properties involved in the search request. It's alphabetical, so body appears quite early here. And you can see that it defines a set of properties that this request has. And at the top here, you can see that aggregations one. So the name here, aggregations, but we also define that alias or aliases that might exist for it. It's not required on the body, and if it is included, it's of kind dictionary, and that has a key which is instance of string, and the value is instance of aggregation container. So these are the pieces of information that you saw in that TypeScript being moved and transformed into a JSON representation. So what's the job of the .NET code generator? Well, the first thing, obviously, we have to read in that schema. So we just deserialize the JSON. Then we start to build up some contextual information about what it's representing. So what are all the endpoints it's defining, what are all the types it's defining. And then we do a further phase where I call it kind of marking and enrichment, and we'll discuss what that does in a second. But once we've got a lot of information built up from the schema and the rules around how we're going to model that in C# that are defined through that sort of marking and enrichment phase, we can then actually build up the syntax tree for each C# file that we want to produce. And we do it kind of file by file. Some files will have multiple classes, some may just have one. So we build up the syntax tree, and then we simply write out the CS file, pretty much as we saw in the simplified example, just it's obviously more Roslyn code. So that marking and enrichment phase is kind of a critical step because some of the things that are defined in that TypeScript don't map particularly well to how we want to do things in C#. So one of those was that underscore global.search namespace. That's not how you would write a namespace in C#. You wouldn't have an underscore, you wouldn't lowercase the first letters. So we transform those. We remove or simplify the namespaces as much as possible. So we don't even bother with the global part because that's not necessary. But we do make sure that the rest of the namespace is correctly cased for C# conventions. We also check whether any of the types that are defined in TypeScript are potentially invalid C# type names. If they conflict with a keyword, for example, they can't be used. And so we need to detect that. And then we have two mechanisms to deal with it. We either have a rule-based mechanism where the rename does a particular sort of pattern to resolve the problem, or we have specific sort of essentially lookups of for this name, as you see it in TypeScript, we want to call it this in C#. Usually those sort of static ones are to provide some backward compatibility with the V7 naming conventions. We then walk the type hierarchy. So what are all of the requests and responses? What are all their properties? What are the types of those? We start attaching things so you can navigate this schema quite nicely through the C# code behind the scenes. We then identify all the relationships. We mark everything that might be used in a request because those need to be user settable properties. We then look for all those containers and the different variant types that we have defined in our spec and work out how we're going to deal with those. So we have to build up some additional information for them. We try and simplify type aliases. So where we had that like index name that was a type alias basically over a string, if we did that, if we modeled that in C# for all aliases, it would end up with a lot of these little wrapper classes that ultimately just wrap one field, a string, and that wouldn't be particularly efficient because of the allocations, and it wouldn't be particularly nice to work with as an API. So most of those we flatten back to the primitive type, the integer or the string. Index name is one of the exceptions to that because we have a richer model for allowing you to parse an index name from a bigger string or to perform other operations on it. We actually model those as a class, and so we don't simplify them. One other scenario is the bulk APIs are a bit special. They don't return regular JSON, they return new line delimited JSON. So we need to know about those serialization needs so we can generate the serializer code for them. So what does the generator code look like in real world? So when we're generating the syntax tree in the code for what is a request in our spec, we actually end up with between 3 and 5 classes that actually get generated. We have a request parameters class that this code generates that is just going to contain all of the possible query string parameters, and it's a way of us making the API easier to work with later on. So this class just needs to know the query string parameters. It follows the same convention though as what we saw in the previous simplified example. Creates a class declaration, adds in this case the public and sealed keyword to it, adds a base type which allows us to attach the inheritance. In this case, request parameters is going to be a manually created file that we have in the project, and then we add the members, in this case all of the query parameters to it. That gets added, that add class just kind of adds that to the namespace that's getting built up behind the scenes. For the actual request itself, we need to model it in two ways. We model it as a regular kind of C# object-based class that just has properties for each of the body properties. And then we have a fluent syntax in the Elasticsearch API that lets you use dot notation to kind of build up a search request more fluently. For the request itself, we just need a regular class. For the descriptor, as we call them, we need a different structure of C# class for that. So this is the request class, but the constructors we have to first pre-calculate, so certain APIs will enforce things on the path that we need to be user provided, and so in that case we'd want the constructor to enforce that rule as well so that users can't misuse the API and create something without enough of the expected data on it. So we first pre-compute the constructors we're going to need, and in this case we then create another class declaration, and then we add a bunch of members to it. That includes those constructors, a bunch of things that are common to all requests, And if we've got a generic property, then we need to add a property that can hold that. Then we add the query string parameters and the body properties. The body properties uses my own factory method, which is a serializable property syntax. And what that factory method looks like is first it does some type resolution. So for the property, it finds the full type spec in the hierarchy or that we've parsed in from the schema so that it knows about the type information and all of our enriching that we did to it. And once we've got that, then it can create the property declaration with the public keyword. Here, crucially, it's adding the JSON attributes needed to control how the serialization of that will work. The JSON include, the JSON property name, which again is sourced from the spec. And then if it's a request type, we add a getter and a setter, because you need to be able to set those things before you send it. If it's something that's used on a response, we make it read-only and have init accesses on there. So ultimately, this is just a small peek into the code base for the code generator, but it's not that much more complex than what I showed you in the basic demo. It's just you need to know about more of the conventions. And the way I dealt with that was through that Roslyn quota website. I would define what I wanted roughly to be able to generate in a C# file in the first place, put that into Roslyn quota, look at all of the pieces that make that up, all of the declarations and the nodes and the tokens, and then model that in little snippets, or in this case, like I did just showed you with like my own little helper method that could make one of those elements up. So before I left the team, I had a working code generator that was generating about 80% of the API sufficiently. And I had a big plan for it, but then I decided to switch teams at Elastic, so I didn't get to work on it. And I'm rather guilty for the code that I handed over to Florian, who's taken over my role on the client's team, because it's clever code, but it's not particularly well structured. So I had some things that I was planning to address. I just never got to do them. First was refactoring. We'll all come across this. If you build something and you're figuring out how it's going to work, you learn a lot along the way. I learned a lot about the Roslyn API, how to be more efficient, how to sort of simplify the amount of Roslyn API code that I needed to write and package it up into reusable sort of functions. So there was a lot of refactoring that I wanted to do there. But I had some sort of grander ideas. So the first one was around making this more usable by non-developers. So right now, or when I left it, if you wanted to change like how a rename occurred and model the rule or the static rename, you would have to do that in the C# code generator code itself. That obviously means it's only a C# developer can really maintain the code generator and adjust how it works. What I wanted to do is actually make it more pluggable. So as well as accepting the schema JSON, it could accept other JSON inputs that would define the rules for renaming or the rules for which endpoint should be included in a particular code generator run. And that then would mean that non-developers could just take this code generator and execute it with a bunch of inputs and then produce hopefully a valid project at the end of it. The other big thing that I wanted to do that I didn't get time to do, and was one of the main reasons that I planned to use Roslyn in the first place, was actually going just beyond the syntax tree API. So one of the other APIs in Roslyn is called the workspace APIs, and these are quite powerful. What these let you do is load up a C# or a .NET solution file and read it in memory and interpret it. So it can actually read the solution file, that will find all of the projects that solution has in it, and then you can work your way through each of those projects and you can inspect the syntax trees of their code and see how they interrelate and basically control everything programmatically that you could do with the solution in something like Visual Studio. And so one of the big things that we could have done and we would be moving towards is kind of being a bit more intelligent. The existing generator basically deleted the generated folder each run and then regenerated every C# file for every type defined on the spec. It wasn't particularly inefficient. It only took about like 50 seconds, I think, to run, maybe even less. But it's a bit sort of a blunt tool, a bit of a brute force way of doing things. What would be better is actually to read in the existing solution, the current version of the client, then read in the spec and see its model, and then you could actually inspect the existing code against the spec and work out what changes are going to occur here, what types are being added or which types are being modified. And then you could even see if some of those modifications might be breaking to C# users. We might remove something in the spec, but we might want to deal with that more gracefully with an obsolete attribute in the C# code for something like that. So we could determine those differences, and also with the workspace APIs, you can actually have Roslyn compile that then in memory. So once you have the solution loaded up, you could ask the compiler to compile it all and make sure that it does compile. One of the steps that's also quite brute force and blunt at the moment is that you generate those C# files, you load up the solution yourself, and then check it compiles by running it locally, or let it do it through the CI process. But it would be nicer if we could actually do all of that as part of the code generation phase, so that we know everything we output is at least valid compilable C#. So that would have been quite powerful. So I learned a lot. I hope I've shared some of the starting points with you if you have this need in your own code base. Some of what I've shown you would be useful if you're also considering getting started with source generators, because it's similar APIs you might be using. A source generator ultimately is going to modify that syntax tree behind the scenes to make changes to code as part of an analyzer and a fixer, for example, would also use that. So leave you with the resources. Again, this is the link to the slide deck if you want to kind of recap on it. The demos that I've showed you are up on my GitHub repository there. Some documentation for Roslyn itself. This is the main one. Yeah, this is my cheat sheet for working out things in the early days, the Roslyn Quota website. I think I did bring it down a few times by pasting in too much C#, but it's generally pretty good. This is the generated code, so this is the actual generated language client. If you want to look at the generated folder, you can see everything that's being generated there. The spec is also online and on GitHub if you want to look at the TypeScript definitions and how how a compiler and stuff works in there. The only thing that isn't public, unfortunately, is the code generator itself, for various reasons. But hopefully the code I've shown you today is enough for you to understand that actually, once you understand what syntax nodes and tokens you need, generating the Roslyn code isn't that complicated. So that's pretty much it. I don't have time for questions on stage, but feel free to grab me at the side afterwards. I hope this has been useful, and thank you for coming.